Welcome back, everybody. Ready to dive into something really interesting.
I'm ready. Let's do it.
All right, so today we're going to take a look at these large language models, LLMs. Everyone's talking about them these days. And we want to see how good they really are at reasoning, especially when it comes to math problems. We found this super cool technical report.
Oh, yeah.
Yeah, it's from the Shanghai AI Laboratory. And they've been putting these LLMs through the ringer, really testing their limits. So are these things all they're cracked up to be? Or are there some limitations we need to watch out for? Let's find out.
It really is amazing how far LLMs have come in just a few years. I mean, we have models now that can generate text that sounds just like a human wrote it. They can even write code and tackle these really complex math problems.
Right. It's mind-blowing. Like, there are even models now specifically designed to solve math. Like, how crazy is that?
Yeah, it's incredible.
But sometimes, I got to be honest, I find myself hitting that regenerate button like 5 times before I get a response that's actually useful from these AI assistants. It makes you wonder, just how reliable they actually are, especially when you need them to be precise, like with math.
I know what you mean, and that's actually a really important point, and it's something that this report from the Shanghai AI Lab really digs into. They're basically challenging the traditional ways that we evaluate these LLMs. A lot of times we just focus on the peak performance, like what's the absolute highest score a model can achieve, but that doesn't really tell us the whole story. It doesn't tell us how consistent the model is.
So it's like judging a basketball player just by their best slam dunk, right?
Right.
Like you don't know if they can even make a free throw.
Yeah, exactly. What we really need to know is, can these models perform reliably over multiple attempts? And that's where this new metric they introduced comes in. It's called GPass at K. Have you heard of this?
I've seen it around. Yeah.
Okay, well, it's kind of like a stress test for LLMs. Instead of just looking at their best performance, it measures how well they do when we demand consistent, accurate answers over and over again.
Okay, so that makes a lot of sense, kind of putting them through the paces. So how did they actually, how did they do under pressure?
Well, one of the things that really jumped out at me from the report was this figure 1. It basically shows this huge gap between an LLM's theoretical potential and how stable it actually is in practice. Like, we see these massive performance drops. Sometimes the accuracy goes down by like 90% when we demand that consistency.
90%.
Yeah, it's crazy.
Wow, that's a huge drop.
It really challenges this idea that a bigger model is always going to be a better model.
So how did they actually test this consistency? Did they just give the LLM the same math problem like over and over again?
Well, they actually went a step further than that. They built this custom benchmark.
Oh, wow.
Yeah, it's specifically designed to push these LLMs to their absolute limits. It's called LiveMathBench, and it's constantly being updated with these brand new math problems, competition level stuff.
Oh, wow. So they're not just memorizing formulas. They have to actually apply that knowledge to new and challenging situations.
Exactly. And we're not talking about your average high school math problems here either. We're talking about problems pulled from some of the most prestigious, like the most difficult math competitions in the world.
Okay, give me an example. Like, what kind of competitions are we talking about?
So imagine something like the William Lowell Putnam Mathematical Competition. It's known for being insanely hard. Like, even mathematicians who have been doing this for years struggle with it.
Yeah, I've heard of that one.
These aren't your straightforward calculations, You need a really deep understanding of the concepts. You got to be able to reason logically, and you got to be creative in how you apply those mathematical principles.
Okay, so that's a seriously high bar.
It is.
So how do these LLMs actually stack up against those Putnam level problems?
Well, that's where things get really interesting. Even some of the best performing LLMs out there, the ones that get all the hype, like Llama and Quinn, they really struggle to maintain their accuracy when they're faced with these real-world challenges. If you look at tables 2 and 3 in the report, they actually lay out all the scores. And it's clear that while these models show some promise, there's still a big gap between their best performance and their ability to solve these tougher problems consistently.
So they can maybe make a few slam dunks, but when it comes to those crucial free throws, they're not so reliable.
Yeah, that's a great way to put it. And, table 4 in the report really drives this point home.
Yeah.
While these advanced LLMs might do well on the easier problems, their ability to generalize that knowledge and apply it to genuinely challenging questions is still pretty limited.
So it's like, are they actually understanding the underlying math? Or are they just getting good at recognizing patterns in the data they've been trained on?
That's the million-dollar question. And it's this question that has some pretty big implications.
Yeah, if they're just pattern matching, can we really trust them to solve problems they've never seen before, especially in areas where the stakes are high, like healthcare or finance.
Exactly. And that's why this distinction between pass at 16 scores, which just look at the best case scenario, and GPass at 16 scores, which measure consistency over multiple tries. That distinction is super important.
So it's like the difference between a chef who can make an amazing dish once in a while versus a chef who can consistently deliver a delicious meal no matter what ingredients they have or how much pressure they're under.
Yes,
So
exactly.
we need LLMs that are more like that consistent chef,
Yeah.
right? Reliable, adaptable, able to handle any challenge we throw at them.
Absolutely. But there's another layer to this that we need to think about. It's not just about the models themselves. It's also about the data they're being trained on. Section 4.4 of the report really dives into this, and it brings up some really important questions about data contamination.
Data contamination.
Okay.
What exactly does that mean?
So let's say you're training an LLM to solve these complex math problems, right? And you accidentally include some of the test problems in the training data. The model might look like it's doing great, but it's really just memorizing the answers.
Also, it's not actually learning. It's just regurgitating information it's already seen.
Exactly. And what's kind of scary is that the researchers found that even a tiny bit of data contamination can have a huge impact on an LLM's stability.
Wow.
They ran these experiments with a model called Quinn and a specific math data set called Math 500-L5. And they found that as they increased the amount of contamination, the model's performance seemed to get better on the surface, but its consistency actually went way down.
So it's like those students who cram for a test the night before and then they ace it, but then a week later they forget everything because they didn't really understand the material in the first place.
Yeah, exactly. And it shows us that we need to be super careful about the data we're using to train these LLMs. If we're not careful, we could actually be putting a limit on how well they can perform in the long run, especially when it comes to dealing with completely new problems they've never seen before.
Okay, so that's a big problem.
It is.
So how do we fix it? How do we make sure that the data we're using to train these LLMs is actually clean and unbiased?
That's the million-dollar question. It's a really tough challenge. But the researchers do have some interesting ideas. A couple of approaches they suggest could really help us tackle this data contamination problem.
Okay, so what are they?
Well, one of the most promising approaches is something called data deduplication. It basically uses algorithms to go through these massive data sets and identify and remove any duplicate or very similar data points.
So it's kind of like making sure that your study guide doesn't just have the same practice problem 5 times in a row. If it did, you might think you're ready for the test, but then when you see the real deal, you completely crash and burn.
Yeah, exactly. That's a great analogy.
So this data deduplication helps to make sure that the models aren't just memorizing the same problem over and over again, which we know can give us this really misleading idea of how well they can actually perform.
Right. And another interesting idea they suggest is to create more what they call out-of-domain benchmarks.
Out of domain. Okay. I'm not familiar with that.
So these are essentially tests that include problems which are totally different from the kind of data the models have been trained on.
Oh, so it's like testing our star chef, not just on their signature dish,
Sure.
but on their ability to whip up something completely new and delicious from a random assortment of ingredients.
Precisely. It's really pushing these LLMs outside their comfort zone, seeing how well they can actually generalize and apply what they know to new situations.
Okay, so that's a really cool idea.
It is, and it's actually where the researchers made a pretty surprising discovery. Yeah, so while they were exploring this whole out-of-domain benchmark concept, they actually found that some of the most common benchmarks used to test mathematical reasoning skills are actually contaminated with problems that are super similar, if not identical, to the problems found in the training data for a lot of these popular LLMs.
Hold on, wait a minute. So they're testing these models on problems they've already seen.
Pretty much. It's kind of like giving students the answers to the test beforehand.
Yeah, that's not really a fair test then, is it?
It's definitely not. It completely skews the results, and it gives us this false impression of how well these models are really doing.
No wonder all those fancy performance metrics can be so misleading.
Exactly.
So that's kind of alarming.
It is.
If we can't even trust the benchmarks, how do we know if we're actually making any real progress in developing LLMs that can actually reason?
It's a great question, and it really highlights how important it is for us to take a much more rigorous and transparent approach when it comes to evaluating these LLMs. We can't just take those flashy scores at face value. We have to dig deeper. We need a higher standard of evidence.
So let me get this straight. We've got this new GPass at K metric that measures consistency. We need to make sure that the training data is clean and unbiased, and we need to develop better, more challenging benchmarks that can actually test their ability to reason. That's a pretty tall order.
It is.
So where does that leave us? Are we even on the right track with LLMs? Or is this whole thing just built on a shaky foundation?
It's a great question, and honestly, I think it's a little too early to say for sure. What we've learned today, though, is that this whole world of LLMs is a lot more complicated than it might seem at first glance. There's a lot of potential there, but we have to be realistic about the challenges, and we have to approach this whole field with a healthy dose of skepticism.
I think a healthy dose of skepticism is good advice for pretty much everything these days. This conversation has definitely given me a lot to think about. I'm still excited about the possibilities of LLMs, but I'm also a lot more aware of the potential pitfalls.
I think that's the beauty of doing these deep dives. We get to explore these really complex topics together. We challenge our assumptions, and hopefully we all walk away with a better understanding.
Couldn't have said it better myself. And on that note, we'll be back next week with another deep dive into a new and exciting area of research. Until then, stay curious and keep asking those tough questions.
Like the William Lowell Putnam mathematical competition.
Oh, yeah.
You've probably heard of it.
Yeah, definitely. It's notorious.
Yeah, it's like insanely hard. Like even like seasoned mathematicians, people who've been doing this for years, they really struggle with it.
Yeah, I've heard that.
And these problems are not just like straightforward calculations. You know what I mean? It's not like just plugging numbers into a formula. You need to really deeply understand the mathematical concepts. You have to think logically. You have to reason through the problems. And you even have to be kind of creative with how you apply the different mathematical principles.
So you're saying these LLMs are basically trying to become like Putnam level mathematicians?
Yeah, kind of. And it's a really high bar to set.
For sure. So how do they actually stack up against these like really tough problems?
Well, this is where it gets really interesting. Even some of the LLMs that everyone's talking about, the ones that are supposed to be the best, like Llama and Quinn, they still have a really hard time staying accurate when they're faced with these kinds of challenges, these real world problems. If you look at the report, tables 2 and 3 show all the scores. And it's clear that while these models have some potential, there's still a pretty big gap between their best performance and their ability to consistently solve these tougher problems.
So they can maybe hit a few home runs. But when it comes to those base hits, those singles and doubles that you need to win the game, they're not so reliable.
That's a great way to put it. And Table 4 in the report really highlights this point. While these advanced LLMs do pretty well on the easier problems, their ability to take what they've learned and apply it to a completely new problem, one that's really challenging, it's still pretty limited.
So it makes you wonder, are they really understanding the math? Or are they just getting good at recognizing patterns in the data?
Right. And that's the million-dollar question, right?
It is, and it's a question with some pretty serious implications.
Absolutely.
Because if they're just pattern matching, can we really trust them to come up with solutions to problems they've never encountered before? I mean, especially in fields where the stakes are high. Like imagine in healthcare or in finance.
Exactly. That's why it's so important to understand the difference between the pass at 16 scores, which look at the best case scenario, and the GPass at 16 scores, which measure consistency over multiple attempts.
Yeah. It's like the difference between a chef who can occasionally create a masterpiece versus a chef who can consistently deliver a delicious meal no matter what ingredients they have or how busy the kitchen is.
Yes, you got it.
So we need LLMs that are more like that consistent chef, right? They need to be reliable. They need to be adaptable. We need to know that they can handle whatever challenge we throw at them.
I completely agree, but there's actually another really important aspect of this we need to consider. And it's not just about the models themselves. It's about the data that they're being trained on.
Okay, so the data they're learning from.
Right. And section 4.4 in the report really goes into this, and it raises some really important questions about what they call data contamination.
Data contamination. Okay, that sounds kind of scary. What exactly does that mean?
So think about it this way. You're training an LLM to solve really complex math problems, but you accidentally include some of the problems from the test set in the training data.
Oh, I see.
So the model sees the test problems beforehand.
That's not good.
It's not. And then when it comes time for the test, the model might seem like it's doing great, but it's actually just memorizing the answers it's already seen.
So it's not really learning, it's cheating?
Basically. And what's even more concerning is that the researchers found that even a small amount of this contamination can really mess things up. It can have a huge impact on the LLM stability.
So even a little bit of contamination can make a big difference.
Exactly.
Wow.
They did all these experiments with a model called Quinn, and they used a math data set called Math 500-L5. And what they found was that as they put in more and more contaminated data, the model's performance seemed to get better and better at first. But when you looked closer, its consistency actually went way down.
It's like those students who cram for an exam, right? They might ace the test, but a week later, they've forgotten everything because they never really understood the material in the first place.
Perfect analogy, and it just shows how careful we need to be with the data we're using to train these LLMs. Because if we're not careful, we might actually be creating a limit on how well they can really perform in the long run, especially when they're dealing with new problems, things they've never encountered before.
So this data contamination problem is a big one. We need to find a way to fix it.
We do.
So how do we do that? How do we make sure that the data we're using to train these LLMs is actually clean and unbiased?
That's the big question, and it's a tough one to answer. But the researchers in this report do offer a few promising approaches, ways to make sure the data is squeaky clean.
Okay, I'm all ears.
Well, one idea is something called data deduplication. Have you heard of that?
I think so, but remind me.
So it's basically using special algorithms to go through these massive data sets and find any data points that are duplicates or that are super similar to each other.
So you're weeding out the repeats.
Exactly.
All right, that makes sense.
And by doing that, we can help prevent those models from just memorizing the same problem over and over again, which we know can really inflate those performance scores and give us a false sense of how well they're actually doing.
Right. It's like having the same practice problem 5 times in a row in your study guide. You might think you've aced it, but then you get to the real test and totally bomb it.
Exactly. So getting rid of those duplicates is one way to clean up the data. But there's another idea the researchers suggest. It's to create more what they call out-of-domain benchmarks.
Out-of-domain benchmarks. Okay, so what are those?
So basically, they're tests that include problems that are way different from the kinds of problems the models have already seen in their training data.
Oh, so it's like taking our master chef, and instead of just testing them on their signature dish, we give them a random assortment of ingredients and see what they can whip up.
That's a perfect analogy.
So we're really pushing them outside their comfort zone and seeing how well they can adapt.
Exactly. And that's actually where the researchers made a pretty surprising discovery.
What did they find?
Well, as they were digging into this idea of out-of-domain benchmarks, they found that some of the most popular benchmarks being used right now to evaluate mathematical reasoning, they're actually contaminated with problems that are very similar, almost identical to problems that are already in the training data for a lot of the popular LLMs.
Wait, so they're basically testing these models on problems they've already seen.
Pretty much, yeah.
That doesn't seem very fair.
It's not. It's like giving students the answers to the test beforehand.
Yeah. No wonder those performance scores can be so misleading.
Exactly. It really highlights how important it is for us to be much more careful and transparent when we're evaluating these LLMs. We can't just look at the scores. We need to really scrutinize how those scores were achieved.
So it sounds like we have a lot of work to do. We have this new GPass, a K metric to measure consistency. We need to make sure the data is clean and unbiased. And we need to come up with much better benchmarks that can actually assess an LLM's ability to reason.
Yeah, it's a lot.
It's a big challenge. So where do we go from here? Are we even on the right track with LLMs? Or is this whole thing just a house of cards built on shaky foundations?
That's a big question, and honestly, I think it's too early to say for sure. But what this deep dive has really shown us is that the world of LLMs is much more complex than it might seem at first glance. There's a ton of potential there, but we can't get carried away. We have to be realistic about the challenges, and we have to approach this whole field with a healthy dose of skepticism.
I think that's good advice for just about anything these days. This conversation has definitely given me a new perspective on LLMs. I'm still excited about what they can do, but I'm definitely more aware of the potential problems now.
I think that's the whole point of these deep dives. We get to explore these complex and fascinating topics together, challenge our assumptions, and hopefully come away with a much better understanding.
Absolutely. Well said. And on that note, we'll be back next week with another deep dive into a new and exciting area of research. Until then, stay curious and keep asking those tough questions.